Thank you, Mihai, for introduction. Thank everyone for coming to my lecture. All right. So this is the outline of my lecture. I'm going to give 3 lectures. So today, first, it's more like warm up, which is kind of I will introduce the mathematical connections between different physical scales. So it's really warm up for the other lectures. And so basically here, what I mean is from quantum all the way to hydrodynamics. Okay, so we'll build up mathematical connections, formally at least, to show the connections. And then second part, I will talk about, I will concentrate on this so-called semi-classical quantum mechanics. I talk about how do we numerically resolve oscillations in quantum dynamics. And second part, I will mostly concentrate the transition from classical particles to mean field. That's the regime between microscopic and mesoscopic, right? How to pass numerically from, say, Newton's equation to kinetic equations. And the method I'm going to specifically concentrate, which is new work we developed in the last year or 2 called random batch methods. And the last lecture, I will most concentrate on multiscale kinetic equations, how to bridge numerically between kinetic equations and hydrodynamics. So that's the plan. And of course, many of you probably have seen this kind of a diagram before. So basically, when we talk about physical modelings, there are 4 essential scales that one usually do. The smaller scale is the quantum mechanics, which is valid at the time scale of 10 to the minus 15 second. That's femtosecond. And spatially, it's like 1 angstrom, which is 0.1 nanometer. So it's like 10 to the minus 10 meter. All right. So in this kind of time and space scales, one has to use quantum mechanics. And then the next level is so-called microscopic scale. That's between a nanometer and micrometer. So there one has to use classical mechanics, for example, molecular dynamics. So their fundamental equation is Newton's equation, Newton's second law. Then in our daily life, usually if you like the weather forecast, or if you take an airplane, usually one use so-called hydrodynamics, a continuum theory. So that's a macroscopic scale, which is typically valid when you talk about space scale in order of meters, and the time is like order of second. All right. Then between microscopic and this macroscopic, there's a level that's called mesoscopic. So that's where this kinetic theory sits. And the fundamental equation in kinetic theory is the Boltzmann equation. So this is more like the level of statistical mechanics. So the 4 scales: quantum, microscopic or classical, mesoscopic or statistical physics or kinetic theory, and then the macroscopic, that's hydrodynamics, continuum theory. All right. And well, if you assume things are the particles are not moving too fast, not in the order of speed of light. So basically, if you ignore relativistic effect, then these 4 equations are basically all you need, all right, to essentially describe basically the matter, any matters in the physical space. All right, that's all the equations that we need. And what they describe are essentially the same problem, but at different scales. Even it's the same physics, but at different scales, you have to use different physical laws. However, that's not the physics, right? If this is external field, then you have to couple these equations with the forcing equations. For example, if you have an electric field, then you have to couple this equation with Gauss's law, Poisson's equation for electric field. Okay, and if you have an electromagnetic field, then you have to couple these equations with Maxwell equations. Okay, So that's why we have equation like Volato-Poisson, Volato-Maxwell equations, Euler-Poisson, and so on. So you couple one of these four equations, roughly speaking, right, with one of these field equations, then you have these systems. So that's essentially all equations we need to know, actually. If you don't take care of this, no relativistic effect. That's all physics equations that one needs to study mathematically. And let me start from the most fundamental equations. So the first principle equation, that's the embodied Schrodinger equation. Okay, so that's the most microscopic equations. Okay, so at quantum level, one has to use this Schrodinger equation. And here phi is a complex valued wave function, okay, which depends on time t. So here we assume that where you have electrons whose coordinate is denoted by y and nuclei, that's the position of nuclei is x. Okay, so we're talking about electrons and nuclei. That phi is the wave function of this. And h is the Hamiltonian, and h bar is Planck constant. I is just the imaginary number square root minus 1. So here h is called Hamiltonian. It has two parts. The first part is the kinetic energy part. So this mj is the mass. So here I have x denote for nuclei, and y is the coordinate of electrons. So the first part essentially is kinetic part of a nuclei. It's only the Laplace with xj. But of course, you assume there's j nuclei, so you have the xj. Each xj, of course, 3 dimensions, so you have n of them. So you add all these Laplacians. Then you have this Hamiltonian, which is associated with the electrons. So again, you have this kinetic energy part of electrons. That's Laplacian yj. Here, j is from 1 to little n. Assume you have little n electrons. The rest are the forcing terms between the particles. All right, so that's a Coulomb interaction between particles. So this is the particle between the nuclear J and nuclear K. All right, so that's the forcing Coulomb interaction between the nuclei. And this is between the electrons, sorry, this is the Y's are electrons. So these are the Coulomb interaction term between the different nuclei. Okay, and here Z's are the charges. And this is the interaction between electrons and nuclei. All right, so that's the entire Hamiltonian for this entire system. So this actually is a linear PDE. All right, mathematically looks very simple. It's just a linear PDE. And the question, well, actually, this is a famous quotation from Paul Dirac. And in almost 100 years ago, 90 years ago, he said that the general theory of quantum mechanics is not complete. Underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. So once you have this embodied Schrodinger equation, essentially, you know everything about chemistry and most of the physics already are governed by this Schrodinger equation, all right? But of course, that's not the end of the story. I mean, the difficult is only that the exact application of these laws leads to equation much too complicated to be solvable. So I mean, these equations are there, but it's very difficult to solve them. Yeah. But of course, you say, well, it's just a linear PDE, right? I mean, we know how to solve linear PDE. So the question is that the size of the problem is just simply too big for you to compute. You don't have an analytic solution, so you have to use numeric computer to solve it. So if the computer is big enough and fast enough, and you are able to solve this embodied Schrodinger equation that I showed you in the previous slides, then actually don't need the other equations. You don't need all these other macroscopic equations. Just solve the Schrodinger equation, tells you everything about the matters, okay? But the only problem is that we are not at a stage that our computer is not big enough and not fast enough to do this. And here we give example why the quantum simulation is completely daunting. It's just simply impossible. If you look at, for example, the molecule of carbon dioxide, and essentially you have to solve a Schrodinger equation of 75 dimensions, all right? And many of us are familiar with fluid dynamic equation, which is 3 dimensional. It's already very difficult, right? turbulence, and so on. It's very difficult. Here we talk about 75 dimensions. For benzene molecules, actually, you have to solve Schrodinger equation 162 dimensions. So now we know the problem is simply our computer is not big enough or fast enough to solve a problem like this. So that's the difficult. Okay. So it's the size of problem, the degree or the number of degree freedom is simply too large. And then you say, well, it's of course, it's high dimension is always challenging, right? I mean, it arises from anywhere. For example, in machine learning, data science, all the problems are studying configuration. All the problem that we face is mainly how to the dimension too large, how to reduce dimension. So there are various ideas. Some of the classical ideas, for example, is to separate the computation of electrons from that of nuclei. Remember, I have this coordinates x and I, right? X stands for the coordinate of nuclei, and Y is the coordinate of the electrons. You try to separate computation of these two, all right? So some of the classical methods include like Born-Oppenheimer approximation, and where you solve the electronic eigenvalue problem, and that building this potential matrix, then you solve nucleonic Schrodinger equation. So that kind of separates the dimension from electrons of nuclei. But that's still very large, okay? And there's other approach like Ehrenfest dynamics, where you solve a coupled system, the quantum system of electrons with the nuclei and so on. And the more plausible computation approach is to take a mean field approximation. Instead of solving n body, you're trying to find a one body approximation, okay, by taking some so-called mean field limit. And along this direction, there are very classical theory like Hartree theory and Hartree-Fock theory and so on. I think that's what Francois Gauss course is going to talk about, right? How to take this limit. And another most successful story along this line, which actually is being used a lot in quantum in chemistry simulation, is this density function theory. And it's a Nobel Prize given about almost 20 years ago. To the development of density function theory. So these are all kind of mean field approximation, where you approximate n-body Schrodinger by some kind of one-body quantum system. And that is 3 dimension instead of dimension 3n, okay, when n is very large. And okay, now we are started this classical mechanics, Newton's equation. Okay, so if you handle quantum dynamics is too much, so let's see what happens at classical level. That's the so-called microscopic scale, and the fundamental equation is something we learned already in high school. It's Newton's second law, F equals ma. So here we consider a lot of molecules, a lot of particles, n of them. So they are governed by this Newton's second law. If you write the equation for it, so the particles qi as the position of the ith particle, and pi is the momentum. Okay. Momentum, the mi is the mass of ith particle. So the first line, of course, is definition, right? It's like dx dt equals velocity. Time derivative of position is just velocity. That's definition. Second line is F equals ma. And the F, all right, is the given usually is some kind of negative gradient of potential. And this is acceleration. P dot, velocity dot is acceleration. Then it times mass. So that's ma. So these are just a bunch of ODEs, right? Which is actually a Hamiltonian system, which looks very simple. Okay, we know how to solve ODEs. Of course, everyone here knows how to solve ODE. The only problem is that this n tends to be astronomical. So just to give an idea how large this n can be. So I stole a slide from the lecture by Pierre-Emmanuel Jabin, all right? So how large can n be? So here are a few examples. For example, one can use Newton's equations, or I mean, to simulate, for example, the universe, the galaxies, and in the astrophysical problem, one can use. We have this, and typically, if you model stars, galaxies, and typically can be 10 to 20, 10 to 25. If you model dark matters, can be 10 to 60 particles. All right. And in plasma dynamics, if you model electrons, ions, and sometimes the n can also range from 10 to 20, 10 to 25. And what particle method, this Newton equation, particle method is also a numerical method. that people use a lot to simulate mean field equations, like Boltzmann equation, Volotsov equation, and so on. And there, nowadays, people can do particles with like 10 to the 9 to 10 to 12 particles. And also, this particle system also arise in biology. In the last 2 decades, a lot of so-called agent-based models will simulate microorganism of biological systems or life science using particle systems. There, the number of particles can range between 10 to 6, 10 to the 12. All right. And also, particle method also can arise from like collective dynamics in social behavior economics. There is a little bit smaller, 10 to the 3, but still okay. So that's the problem with these particle simulations, and it's simply too large for us to put this system into the computer, because n can also be too large. And then I say, well, I don't care about all these positions. I mean, we have 10 to the, I don't know, in our real life, 10 to 23 particles in the air in our room. I don't care. I mean, the particle number 1 million, or who cares about this individual particle, right? Sometimes you only care about its distribution, density distribution. So that's what the kinetic theory is about. It's describe the particles in the macroscopic level. So here we care about the probability density function, F, which depends on time t and the particle position x and the velocity of particle v. All right. So here we care about statistical behavior of particles, not the individual particles, but it's the statistical distribution. So that F is governed by this Boltzmann equation, and the left-hand side is transport. The particle with velocity v will transport in the x direction by the velocity v. And the right-hand side is a collision term. So these particles, they will interact, okay, they will collide. So the right-hand side is a very complicated collision operators. And I'm not going to give it details today, but later we'll see that a lot. And this collision, of course, had to satisfy certain laws, for example, conservation laws, because these collisions are elastic collisions. So they conserve mass, momentum, energy. Okay. And a fundamental law with the Boltzmann equation is this entropy H theorem, where F log F is entropy. So the entropy actually dissipate, okay, through the dynamics. And if you visit the tomb of Boltzmann in the suburb of Vienna, you will see he has this entropy in his tomb. So that's the dream of physics. When you after you die, and you have some formula that can be carved into this tombstone. That's the greatest achievement. However, the Boltzmann equation, because for F depends on t, x, and v, and x and v are all 3 dimensions, so you still have to solve essentially a 7-dimensional problem, which in some sense is still too large. Okay, it's too large. So then it comes from to the fluid dynamics, which is what we said is the macroscopic scale. All right, and the fundamental equation in fluid dynamics, of course, the Euler equation or Navier-Stokes equation. So this equation basically just 2 components for these equations. First is 3 conservation laws: conservation mass, conservation momentum, and conservation energy. So that's given by this nonlinear partial differential equations. So here rho is the density, rho times u is the momentum, and u is the velocity, and E is the total energy. Okay. Of course, here you have a looks like 3 equations. That means 3D is 5 equations because u is 3D. But you have other things, right? You have rho, u, and E. Then you have this P here. So the equation, this is Euler equation, right? The right-hand side is 0. And the P is called pressure. And you have to write P as a function of other equation to close this equation, right? You have more variables than more unknowns than the equation. So you have to connect P with the other variables, E and rho and U and so on. So that's called the equation of state. So basically, fluid equation has 2 components. One is 3 conservation laws, and then you have this equation of state to close the equation, or constitutive relations. Okay, so then you get the closed equations. So the Euler equation, which is described ideal gas, is just this equation. But if you add so-called viscosity and heat conductivity, you have the Navier-Stokes equation. All right. So that's fluid dynamic equations, which are defined as physical space. So these are 3D. In terms of computational cost, this is the minimum because it's 3D equations. All right. So computationally, they are more affordable to solve kinetic equation, I mean the fluid equation, than any of the other equations that I have talked about. All right, so now you have seen all the fundamental equations in all different scales. And then the question is, all right, so as I said, all these equations can describe the same physical phenomena, but at different scales. Then you wonder if they describe the same physics. The only difference is that they are used in different scale. There must be some connections, right? If all these equations are correct, there must be connection between these two. So in other words, one should be able to derive mathematically from equation in one scale to the other. There must be some mathematical connection. You can derive one from the other, all right? Because they are supposed to be describing the same physical phenomena, okay? So of course, explore these mathematical connections when in some rigorous way. Of course, physicists understand these connections, but for mathematicians, we want to understand this connection rigorously. And the study of these connections actually helped generate some of the most exciting results in mathematical physics and PDEs, right? So some of the results which study these transitions were some of the most important results in PDEs. So of course, this rigorous connections was not, well, it's not new, right? I mean, already in this famous address by David Hilbert, in the International Conference of Mathematicians in year 19,000. And what I just mentioned was actually what's now known as the Hilbert sixth problem. Essentially, what he want to do is axiomatize physics, all right? So you want to understand the transition from microscopic physics to macroscopic physics. And so at the microscopic equation, as I said, it's a system with many degrees of freedom, all right? But at the macroscopic equation, like hydrodynamics, there are much less number of degree freedom. So how a many degree freedom system can eventually come to a small number of degree freedom system? Another interesting phenomenon, of course, at both quantum level and the classical level, these are all Hamiltonian systems. So it's time irreversible, all right? You can go backwards in time. But at the kinetic level, as I see, we have this H theorem, we have inequality, all right, not equality. And hydrodynamics, we know that here you have second law of thermodynamics. All these systems are time irreversible. So how you start from a time irreversible system, you end up at time reversible system. So these are all the mathematical mysteries that Hilbert was curious about, and he really wanted mathematicians to study these problems, all right? And he himself actually spent some time to work on this. For example, he tried to understand the connection between kinetic Boltzmann equation and hydrodynamics. And he even invented what is now known as Hilbert expansion by doing asymptotic expansion from kinetic, and he can sort of derive at least the Euler equations if it's Maxwellian gas, for example. So he worked on this, okay? And all right, so now basically I would describe these transitions. I want to just show you how you connect these different scales mathematically. Of course, I will introduce just the formal connections. The rigorous mathematical connections is very hard. I mean, we will hear some of this mathematical work in this week from some of the other lectures. So let me start with quantum mechanics, and I want to see how one can pass from quantum mechanics to classical mechanics. This was done actually by a beautiful weapon invented by Eugene Wigner. He's a Nobel laureate. So let's start with this Schrodinger equation. All right. So to simplify notation, I just represent this potential by V function of x. All right. And here, well, mathematicians, we have to if you non-dimensionalize the Schrodinger equation. And then you instead of h bar here, you end up at the epsilon. Okay, so from now on, I may use interchangeably epsilon or h bar. I mean, depend on different circumstance. When it's the dimensionless, I use this epsilon, which is dimensionless parameter semi-class scaling. And when epsilon is large, it's order 1, we sort of in the quantum regime. When epsilon becomes very small, so that's what we know as the classical limit. All right. So we start with this dimensionless Schrodinger equation, and this is the Wigner transform, which is essentially it's a Fourier transform, but on this quantity. All right, on this u, on this quadratic quantity, u is a wave function, u and u bar is complex conjugate. And of course, this they are at different physical locations, x plus some variable and x minus the same variable. So you take Fourier transform on this eta variable. Then you end up at the quantity w, which is depending on this psi, is like a wave number in for like Fourier mode, right? Psi, and it still depends on this x. So actually, this u times u bar is the density matrix. Okay, so you take Fourier transform on the density matrix, you get this w, which is called the Wigner function. Then if you satisfy the Schrodinger equation, w satisfy this equation, which is usually called the Wigner equation. The Wigner equation, as you can see, is w depends on t, x, and psi. So the left-hand side is actually the transport operator. Okay, so if you don't have this v, if you have so-called free Schrodinger without the potential, then W actually satisfies this very simple linear transport equation. And now this V term gives rise to this actual term. Theta, which is defined here, is actually a pseudo differential operator. Okay. And it's a kind of scattering term where this delta V is just this finite difference of V at a different location. So if you satisfy the Schrodinger equation, this W satisfy this Wigner equation, which is a closed equation. Okay. Then you say, why we need this? I mean, W actually is defined in phase space, right? The U is defined in physical space. Now, psi has same dimension as x with double dimension. So why you need to go to this crazy equation in high space? Well, now actually, when epsilon is very small, okay, epsilon is like Planck constant. When epsilon is very small, you can do a Taylor expansion on this term. Then clearly, Taylor expansion around the second term. You Taylor expansion at x. Then you can see the leading order, these two 10 terms cancel, right? Because they are both v of x. And the next order, you get this gradient v times all the epsilon and cancel this epsilon, all right? And if you plug this asymptotic Taylor expansion into here, and formally, when you go to 0, this term and this theta term, this non-local term, actually collapses into this very simple term, which is the x gradient of v, okay, times this. So here is this simple transport equation, a transport operator, and on this right-hand side, which comes from this potential, become this equation. And this actually is the classical Liouville equation, which is the that's probability density. That's the equation for probability density function of a classical particle. To see that actually this is a linear velocity Liouville equation, and if you define its characteristics, all right, this is a linear transport equation. So you have x transporting psi here. Oh, sorry, it's typo. This should be transporting x. Here you have transporting psi. So if you introduce the characteristics or by characteristic, because we have x and psi, if you define dx dt equals psi and d psi dt equals this, this is the forcing term, force, all right? Minus gradient is force. This is just Newton's second law. This is exactly Newton's equation. Here, of course, the mass of sum and the mass is 1. So now you see if the epsilon is basically Planck constant. If Planck constant goes to 0, quantum mechanics actually becomes classical mechanics. And Schrodinger equation collapses into the Liouville equation. And you can see that from this Wigner picture. So what's nice about this Wigner transform, you can see this transition from quantum mechanics to classical mechanics in a very simple, straightforward way. Okay. And essentially, we know at quantum level, we have waves, right? These are the precise wave functions, which is highly oscillatory. And the epsilon actually is the wavelength of this psi, wavelength. So while this classical mechanics, even go to 0, essentially the particles are essentially the wave packet, all right? So we talk about particles, the envelope of these oscillations. Those are the so-called particles. So when you go to zero, and this wave packet actually is governed by this Newton second law. So that's the tradition between quantum and classical mechanics. So here are some of the fundamental works in this direction. All right. Well, they did it a little more general. They coupled this V with the Poisson equation or Hartree equation. So you can, I mean, these are some of the works that which establish this kind of so-called semi-constant limit rigorously. All right, so that's the story, how to pass from quantum to classical. Now, suppose we want to understand the transition from classical mechanics to Boltzmann equation. All right, so now I start with this embodied Newton's equation. Okay, again, now x is the position, v is the velocity. So I assume the mass is 1, okay? So this is Newton's equation. Now this forcing term comes from this phi is the interaction between different particles, all right? Usually it's binary interaction. For example, in the Newton equation, you have Coulomb interaction between particles. Okay. So that's Newton's equation of embodied. So here I introduce the z1 to zn, which are the coordinates of all m particles, including both the position x and the velocity. All right, so I denote those by z. And you can also introduce the probability, the density function w, which depends on all the zn. All right, so it's equation 3n times 3n. So if x and v satisfy this Newton equation, or if z satisfy Newton equation, then of course wn, as I showed in the previous slides, Wn satisfies this Liouville equation, all right? And Ln is the Liouville operator, which has this transport part and this forcing part, okay? All right, so we start with this Liouville equation of this Wn depends on the 6n variables, right? You have 3n from x, 3n from x, and another 3n from the velocity. So it's a very high dimensional embodied equation. We cannot solve it by computer. Okay. And now what you do is actually we send n to infinity because n is so large that we just treat it as infinite, n like 10 to 23, right? In the air, a molecules. We send n to infinity. That's called the mean field limit. All right. Of course, when I send infinity, the w depends on variable 3n, 6n. Of course, when n goes to infinity, you have infinite number of variables here. I cannot do that. What we do is we integrate out. Now we define so-called marginal distribution. So for here, the j is marginal. We integrate out zj plus 1 all the way to zn. Okay. Now you only have the remaining variables are z1 to zj. So integrate out. So this fjm is called a marginal distribution. Okay. And we have to make some assumptions. First of all, we assume all these particles are the exact same. They are identical. There's no difference between them. We treat them very equally. So which means you exchange the variables. In W depend on the z1 to zn, right? If you exchange zi with zj, it does not change wn. Okay. Another important assumption is so-called molecular chaos assumption. So assume that if you treat this f is like a probability density function, they are all independent. So for example, if you consider two-body distribution, then they can factorize into a product of a one-body distribution like this. So that's called a molecular chaos. Okay. And now we still have to take a limit. Of course, when we take anti-inlet limit, imagine you have all these particles in a box. If n go to infinity, if you have the same size of particle, then your box is not big enough to fill out all the particles. So we send n to infinity, you have to assume that each particle has diameter epsilon. You have to send it to 0. All right. Otherwise, your box is not big enough to hold all so many particles. So you send n to infinity, you have to send the epsilon to 0, but you have to send them in some special way, right? You have to make sure that n, it should be capital N, sorry. Capital N times epsilon square is a constant, basically it's bounded. So under this assumption, so this limit is usually called the Boltzmann-Grad limit. Then one can show this one-body distribution solve the Boltzmann equation. Okay, so that's how we arrive at Boltzmann equation from Newton's equation. And of course, mathematical proof of this limit is incredibly difficult. All right, there are some landmark works. Well, the one by Longford in 1974, and more recent progress by Gallagher, Saint Raymond, and you can, if you're interested in topic, you can read this book. It's called From Newton to Boltzmann, okay, for hard spheres and short range potential. And unfortunately, this limit is the mathematical proof of this limit is valid for a very, very short time. It's for fraction of mean free path. I mean, the mean free path is the average distance between two collisions, right? So this limit is valid even before a collision even happens. So it's a very difficult fundamental work, but unfortunately, physically is far from being satisfactory. And I think, well, I mean, Mario Pugliese is a leading expert in this business of this mean field limit of kinetic Newton equation. He's going to cover some of this, the work in this direction. All right, now, so once we have the Boltzmann equation, now I'll say, okay, how do we go from Boltzmann to fluid limit? So here's the Boltzmann equation. And now it scales the Boltzmann equation such that we have 1 over epsilon, and here epsilon is so-called Newton's number, which is essentially the mean free path. So that's average distance between two collisions of particle divided by a typical length scale, say the size of the domain, all right? So that's dimensional number, it's called Newton's number. So now, to connect F with hydrodynamics, we take so-called moments. So we integrate F depend on T, X, and V. V is particle velocity. We integrate over V, so that's so-called the density, all right? And integrate F times V, that's the momentum. So it's a U is velocity times the density, that's the momentum. And the so-called second moment, we allow you to define the temperature. Okay. So basically, the connection between the F and these macroscopic variables in fluid dynamics are through these moments, okay? And because this Q, as I said earlier, certified as conservation mass and momentum energy. So mathematically, what it means, if you multiply this equation by 1, V and V squared, that's give it the moments. And you integrate over V, the right-hand side should vanish. So therefore, you end up, if you do what I just said, multiply this equation by 1, V and V squared over 2, and then integrate, the left-hand side actually gives this equation. The first term in particular, by our definition here, is exactly the time derivative of mass, momentum, and total energy. And the next term gives you this divergent flux term, okay? The right-hand side vanishes because of this conservation. All right, so that's basically this is known as the moment equation. So these are the moments of F, okay? You have this moment equation. However, if you look at these equations, and you have N and U and E, right? 5 variables here, because U is in 3D. But you have this P and Q. And P is the stress tensor and Q is heat flux. So it looks like you have more unknowns than the equations. So these moment equations are not closed. Okay, they are not closed. So therefore, you cannot replace this 6-dimensional problem by simply a system of 3 dimensions for free, because you have more unknowns. You have higher order moments. Here you have the lower moments, but you have these things that need higher moments. So you cannot close it. And the only way to close it is to send this epsilon to 0. So imagine that epsilon is mean free path. So when mean path go to 0, it means all these particles are kind of packed each other. It's very much like you have a traffic jam, right? If usually during a nice time you go to highway, there are a lot of cars. Your cars are particles, they are far apart. But in traffic jam time, like in the peak time, the cars are bumper to bumper. So that's where you see it's continuum regime, it's fluid dynamics. Okay, we say traffic flow. That's what flow means. When mean free paths go to 0, then actually one can show the collision term has the property that when epsilon go to 0, F converge to this function M, which is so-called local Maxwellian, and the M only depends on N, temperature T and U, and I mean only depend on these moments. So this M only depends on this macroscopic quantity, and for this special F, okay. For this special F, then this P and Q can be expressed as a function of these 5 unknowns. Then you have 5 equations, 5 unknowns. Then you close this equation. Okay, you can close this equation. And that closed equation is exactly this compressible Euler equation. Yeah. So the fluid dynamics is basically mean free path, zero mean free path limit of kinetic equations. Of course, you say, well, actually, of course, epsilon is not really zero. It's small, but not zero. And if you do a more careful example, if you expand the solution to all the epsilon, then you can get the Navier-Stokes equation, actually get this extra term. Instead of the right hand side 0, you get the viscosity term and heat conductivity. So that's how one derive a Navier-Stokes equation from Boltzmann by expanding to the next order. And the expansion is called a Chapman-Segal expansion. It's non-trivial expansion, but you can get it. All right. Then again, the rigorous justification of this limit is very, very difficult. And actually, only incompressible Navier-Stokes equations can be rigorously proved. So that's a program that started by the celebrated work of Bardos, Gauss, and Livermore, and was completed by the milestone work of Gauss and Saint-Raymond, okay, but only for incompressible limit. All right, so now I've shown you the mathematical transitions. Now you have seen, right? Start from quantum to classical to kinetic theory to fluid dynamics. We have shown you at least the formal level how one can derive and find the connection between different scales. To give you a simple summary of what I just talked about. So essentially, all these macroscopic equations are the limits or asymptotic approximations of microscopic equations. Okay. And the microscopic equations, actually, they are linear equations, right? I mean, Newton equations are linear, but if you write Liouville equations, they are linear, okay? So microscopic quantum Liouville equations are linear. So in the mathematical theory, it's relatively simple because they are linear PDEs, and they are time reversible. However, this mesoscopic or macroscopic equation, Boltzmann fluid equations are nonlinear, but they are time irreversible. So you see the fundamental difference. So therefore, well, computationally, the microscopic equations are harder for computation because there are too many degrees of freedom. All right, the problem is too large to put in a computer. But the macroscopic equations are harder for analysis because these are all nonlinear PDEs, right? Mathematics to prove any theorem is very difficult. But numerically, it's easier because the degree of freedom much less than okay. So therefore, they are. I mean, it's very funny that the microscopic ones, mathematical analysis can be easier, but the numeric is hard. Macroscopic are exactly opposite. Okay. And we know, I mean, one of the millennium problems is to really to understand the regularity of the incompressible Navier-Stokes equation, right? So you see how hard it is. Oh, so okay. So I hope by now at least you get an idea of how, I mean, these transitions, the connection between all these different laws, physical skills, all right? And now let's come to, you say, why we care about this so-called multiscale problem, okay, multiscale computation. So there are a few examples where a lot of problems we do encounter multiscale phenomena. The most famous one, of course, if you simulate, for example, space shuttle reentry problem. So the space shuttle that if you go to, I don't know, Moons or Mars, right, to the out orbit, which when the altitude is very high, the mean free path is very large. All right. So if the the space shuttle is like in the 100 kilometers above us, there the mean free path is in the order of 1 meter. So there the molecules are so rarefied. The air is so rarefied that the particles barely see each other. They barely collide actually. It's called free streaming. But on Earth, where the air we breathe now at our altitude is like 10 to the minus 8 meters. So you see the sharp transition of the mean free path changes in many order of degree of magnitude, many order of magnitude. All right. So you really have to solve a multi-scale problem. And if you solve like super, if you use Navier-Stokes equation, then you find, well, if Mach number say is bigger than 1.4, the thickness of a Navier-Stokes equation, of shock profile of Navier-Stokes equation actually is not correct. Okay. And if you do so-called, for example, if you study the dislocation problem, okay, and then if you have, for example, you have crackers, You have cracks. And at crack, near the cracks, actually, the continuum limit not continuum mechanics not valid. You have to simulate molecular dynamics at cracks. And if you do chemical reactions, for example, chemical reaction, you cannot use Newton's equation, molecular dynamics. You have to use quantum mechanics. All right. So there are a lot of problems in your real life where you have to face the multiscale problem. Of course, you can solve a Schrodinger equation. That's the end of it, right? We don't need a multiscale simulation. The question is that microscopic simulation is simply too expensive to do it. That's why we need to combine microscopic with macroscopic simulation. That's called a multiscale simulation. Okay. So there are different methodologies for multiscales. The most straightforward one is said, okay, all right. So for example, if you consider multiscale between kinetic and hydrodynamics, you can say, well, for example, if you want to simulate the specialty entry, you say when the attitude is not very high, you can use Navier-Stokes equation. When it's very high, use kinetic equations. All right. And then, of course, here is a computation less expensive because it's only 3D. So I do this coupling. Okay. However, it's very difficult to couple these equations because you have to put some interface here. It's artificial interface to connect these two equations. Well, it's dynamic. First, you don't know where to put this interface. All right. How do you decide this is a hydrodynamic regime, that's kinetic? And second, if you know where to put this interface, you have to connect these equations by some kind of boundary condition or interface condition. That's not so easy because, well, we know, as I said earlier, from kinetic to hydrodynamics, if you know F here, to get the moments is easy. You just take moments, right? You take the integral in V. That's easy. Well, so from micro to macro is easy. You should take average, you take moments. But the other way around is not easy because here, if you here is you know the average. From macro to micro is not easy because from average to pointwise, if you know the average function, you know the pointwise value. That's impossible, right? There's no unique solutions. So that's the challenge for multiscale problem. I mean, you have to transfer data from microscopic to macroscopic. One direction is very difficult, okay? Of course, there are some works in this direction, some earlier work by Noisy, Clark, Patton, and so on, where they just simply assume the interface is a local equilibrium. So I assume, for example, it's already local Maxwellian, all right? Once it's local Maxwellian, then I define F to be more local Maxwellian. If I know the moments, I can define local Maxwellian. So that's my F. I use that F to define here. Okay. But there are other issues. For example, this interface condition, if you connect this interface condition, is this problem well posed? Suppose I use some interface condition. Then I have to study mathematical well posedness of this, which is very difficult. Okay. Very difficult problem. And the second strategy is so-called heterogeneous multiscale methods. All right. So here's the idea. I used this is a picture I used from the paper from Weinan and Enquist. So here we have a macroscopic mesh. Say, suppose we solve fluid dynamic equation on this mesh. But my consider relation or equation state has to be simulated from the microscopic level. All right. Because I don't have the closure. I don't have this equation state. So I have to obtain equation state or consider relation by solving, for example, Boltzmann equation. So locally here, at each of this macroscopic value, I have this microscopic mesh where I do a kinetic simulation. Okay? And the kinetic simulation supply the consider relation. Then I solve this moment equation. So that's called heterogeneous multiscale method. Well, there's this classical work where you couple basically quantum mechanics with classical mechanics. Remember, we can do molecular simulation by solving Newton's equation. But to solve Newton's equation, you need this F, the forcing term. And if you have things like chemical reactions and you don't have forcing term, you have to get forcing term by solving Schrodinger equation. Okay? So the idea of this classical work, which eventually won the Nobel Prize in chemistry by Kaplas, is to you do quantum simulation to get this force F, this V potential. Then so once you have this V, you take minus gradient V, that give you F, then you solve Newton equation. Okay. So these are all type of so-called heterogeneous multiscale method. Locally, you solve microscopic models. But again, the difficulty is that for example here, if you only know the average macroscopic value, how do you solve this kinetic equation? You need boundary conditions. So you need to go from macroscopic to microscopic transition, which is the bottleneck of this kind of for equations. All right. In some special situation, you can pass from macros to micro, but in general, this is very difficult to do. And the last computer methodology that I'm going to talk about during this school is the so-called asymptotic-preserving scheme. And the idea is that I want design scheme which works in different regimes, in different scales, all right? But I'm only going to solve one equation. I'm not going to use two equations. I just solve one equation, the microscopic equations. But I hope I have a microscopic solver. I hope this microscopic solver automatically becomes a macroscopic solver in the macroscopic limit when I cannot afford to resolve the small scale, okay? And it's very much like so. Suppose I want to have I want to go fish. I want to fish shrimps. So I have this fishing net. Your fishing net is more like your mesh has to be smaller than the scale of a shrimp, right? Because if you use very large, too coarse mesh, I mean, all these shrimp will drop, and you may get something that's garbage. It's not something you want. However, if you design a scheme such that although I use very coarse mesh, I do not catch a shrimp. I catch a lobster, which is a macroscopic version shrimp. I'm still very happy. So that's the best I can do. We're going to miss all the shrimps, but I'm going to capture lobster. So I want to have a scheme which has this capability. Okay. So essentially, why it's called asymptotic preserving? Because I want a numeric scheme to preserve the asymptotic transition from micro to macro. That's why we need to study how the mathematical transition between these scales, which guide our design of numeric schemes. Okay. And this is a diagram which you have seen a lot. If you, you probably have seen this kind of diagram. So essentially, the why this kind of idea works. So essentially here, suppose I have a microscopic model, Fe, depend on small parameter epsilon. When epsilon goes to 0, I get a macroscopic equation. For example, if this is a Boltzmann equation, when P fast go to 0, I get Euler equation. All right. So now I discretize this equation with a numeric parameter delta. That's my mesh size, time step, and so on. Of course, typically when delta goes to 0, it should convert to this. But in reality, my delta I cannot afford delta to be smaller than epsilon. All right, it's too expensive. Actually, what I do is my delta is going to be larger than epsilon. So relatively, that's like epsilon go to 0. I fix delta, let epsilon go to 0. What happens? Then I can take a limit of this scheme. I fix delta, let epsilon go to 0. I end up some scheme which depends on delta, but not depend on epsilon, no more epsilon. If this scheme is a good approximation of these macroscopic equations, then I say the scheme is asymptotic preserving. So essentially, I end up at a scheme which can solve, effectively get a solution of Euler equation correctly. Right? That's my lobust, all right? So this is my shrimp, this is my lobust. So I have a scheme which allows me to capture the solution of lobust. So that's what this scheme works. They say why this idea works. So here's a very simple argument that I had with Francois Gauss and Livermore 20 years ago. So this is why it works. So look, if you solve, well, mathematically you can say, okay, the distance between F epsilon and FO say is like all the epsilon, all right? And now if I have a numeric scheme here, then if you do a standard convergence analysis, you compare this with that. Typically, suppose I have R's order scheme, so you have all the areas delta to the power R. But unfortunately, I have this equation here that says 1 over epsilon in front of the collision. So your area will be divided by epsilon to some power. Okay, so that's very bad when delta is larger than epsilon. This is very bad. Okay. However, if the scheme is AP, which means that the distance between this guy and that guy is all the epsilon, but uniform in delta. Okay. And so from here to here is this distance between this and that is all the epsilon, and this guy is a good scheme for this macroscopic equation. Then the distance between this guy and that guy is all the delta to some power, say gamma R. Then my new area is I have one area analysis based on this and that. That's this guy, which is very bad when it's small. I have another area which is basically I just do triangle inequality, add this area from here to here and there. Get another area. You have all the epsilon here, all the epsilon here, all the delta to the power r there. You get a second error, epsilon 1. And then one error is very good. Epsilon 1 is very good when epsilon is small, but very bad when epsilon is large, epsilon 1. The other error is very good when epsilon is large, right? But it's bad when epsilon is small. So I have these two different errors. Clearly, both errors are correct. So what I'm going to do, I'm going to take smaller one of this error. And the worst case scenario happens when they cross, right? That's when the epsilon is essentially delta of r over s squared plus 1. So you plug this epsilon into here or there, they end up at something, you get rid of the epsilon. When epsilon equals this, you put it either here or there, because at here they cross. Then the right-hand side, you get rid of the epsilon, you only have this delta with a positive power. So that means actually this error between this guy and that guy is a uniform epsilon. Okay? So you see, if it's AP, you get a uniform convergence. All right? The AP scheme has a uniform convergence, which means I can take delta based on my tolerance, not because it has nothing to do with epsilon. But in reality, of course, delta is smaller than epsilon, I get a solution of the Boltzmann. When delta is larger than epsilon, I get a solution, I get only lobus, right? I missed some details, but that's the best you can do. You get a Macroscopic equations. So that's the argument why this idea can work. And I'm near the end. Actually, I don't have time. Now, the question is, can you always do this, right? Can you always design scheme which is AP? Which means that can I always have scheme which allow me to take the mesh size times the much larger than epsilon? So I talk about all three different scales, right? From quantum to classical, from classical to kinetic, and from kinetic to hydrodynamics. So I have tried all these different problems. I have some good success stories and partial success story. For example, if you only use this methodology to bridge the gap from quantum to classical, the answer is you want to have a discrete Schrodinger when Planck constant goes to 0. You hopefully, if it's AP, you should end up a discrete lower equation. That's what AP scheme means. And it turns out you can design scheme which allow you to do this. You allow time step to be larger than epsilon. Yeah, that you can do, but for space it's impossible. So it's not we can get AP in time, but not in space. Well, how about what the best you can do in space? In terms of the best you can do in space is the best you can do is that x to square root of epsilon, right? It's not epsilon. A naive approximation, you need delta x to be epsilon, but if you do some, here's the method, Gaussian beam, Gaussian wave packet method, which allows you to do delta x to be square root of epsilon, which is better than epsilon, but not all the one, okay? And then the discrete, if you start with classical mechanics, you have discretization of Newton equation. When n go to infinity, when the particle number go to, hopefully you can get the discretization of Boltzmann, right? And recently we have some successful story on this, for molecular dynamics. By this method we call the random batch method. That's what I'm going to talk about next time, all right? And turns out the most successful story of AP actually is in the area of kinetic theory. And if you start with discrete Boltzmann, when the mean free particle goes 0, you hope you can recover some nice discretization of Euler or Navier-Stokes. For this regime, actually, AP has largely been successful. You can do this design for both space and time. So that's essentially what happens, the current status for state. Well, originally, I hope I can do this, but I will leave this to the next lecture, from quantum to classical mechanics. So I will stop here, and any questions?
Okay, thank you very much, Shi. So any questions? Some comments? So I have one question, Shi. So you said that in the proof of Gallagher, Saint-Raymond, Texier, this proof is valid only for a fraction of the mean free path. So what is the main difficulty of this proof? Is some technical point, or
well, for this, I'm not an expert on this, right? So I would I think the talk of Mario probably will touch some of these fundamental difficulties of this.
Okay.
So thank you for your presentation. So I know what was the contribution from Goltz and from Goltz, Bardos, and Levermore to the derivation of hydrodynamics from the Boltzmann equation. But what was the contribution from Laure Saint-Raymond and Goltz, I think, in 2003?
Yeah, there was some gap in the original Bardo Gauss Levermore. I think they assume some local moment conservation, which was eventually removed in the work of Gauss and Saint-Raymond. Actually, I will start from where I ended last time because I didn't finish my talk last time. So we're going to talk about the so-called asymptotic-preserving schemes. All right, so it's basically we try to design a scheme which works across in scales. So it's based on solving microscopic equations, but I hope it works even in the macroscopic scales. And the idea is to try to preserve the asymptotic transition from micro to macro scales, also at the discrete level. All right. So basically, this graph shows you that if you have a physical model which may depend on some small parameter, when you go to 0, this microscopic model becomes a macroscopic one. And now you discretize the microscopic equation with this numerical parameter delta, which may be time step and mesh size and so on. And you take the same limit, but for the scheme, okay, set equal to 0, fixed delta. You end up some scheme, which hopefully is a good scheme for this macroscopic equation. All right. So that's what it means to be asymptotic preserving. So you have discrete analog from this continuous limit from micro to macro. And what you want to achieve is that you hope when epsilon is very small, you can take a mesh size time step, which is much larger than a small scale. So what it means, remember last time I talked about 3 limit from quantum to classical, from classical to kinetic theory, from kinetic equation to fluid equations. So basically, we want to preserve these asymptotic limits numerically. So basically, what it means is that if you start with the Schrodinger, you have discretized the Schrodinger equation. You hope when this epsilon, which is h bar, go to 0, your continuous limit is this lower equation, but you hope you have a discrete Schrodinger. You take equal to 0, you end up at some discrete lower equation. All right, and then you try to do similar things if you pass from Newton lower equation to discrete Boltzmann. When the say particle number n go to infinity, and if you start with discrete Boltzmann and you pass let the Newton number go to 0, you hope you end up some kind of discrete Euler or Navier-Stokes equation. So what we cover are essentially all these 3 different cases, and this AP strategy has been successful for some of this, but not for all, right? So today I will start from this quantum transition to classical. So it turns out that we can get this requirement for time, but not for space. So today I first start from this, then I probably will also talk a little bit about this. All right, so I will start with the transition from quantum to classical mechanics. And we all know the difficulty of doing quantum simulation. As I said, ideally, if you can solve embodied Schrodinger, then you don't need to solve other equations because Schrodinger equation give you everything about the properties of matters. However, the major difficulty to do a so-called quantum simulation or first principle simulation is that first is n, which is the number of particles, is very large. Can be easily hundreds of dimensions. So that's known as the curse of dimensionality. All right. Another difficulty is that the Schrodinger equation is valid in a very small scale. So at the beginning of last lecture, I mentioned it's valid on a scale of Armstrong, which is like 10 to the minus 10 meter. All right. And Schrodinger equation actually is a wave equation, so solution highly oscillatory. So these oscillations cause you a lot of trouble. So if you combine large and small h bar, so that's just too much for the computer to solve. All right. Of course, here today I'm not going to talk about this difficult because that's another difficult. I'm not going to say much about this. I will concentrate on this difficult small h bar problem. Essentially, I try to see whether we can overcome the constraint due to this highly oscillatory nature of the solution. So I'll start with Schrodinger equation, write it in a very simple form. So U is the wave function, all right, and the epsilon is the wave. It plays a role of a Planck constant, but it has been non-dimensionalized. So it's represent a small semi-classical scaling or the wavelength. V is just the potential, which depends on x space, and we'll give some initial data. All right. So now, if there's no potential V, then you can solve this equation analytically. Say if you use, for example, if you use a Fourier transform, right? Then if you do a Fourier transform on space, you get an ODE in the Fourier space. Then you can solve it by hand. In particular, you can, there's a so-called single plane wave solution. So this is the solution to this equation when V equals 0. As you can see from here, you have e to the I over epsilon. Then here is a function of x and t. So from here, you see that you have x over epsilon, e to the I x over epsilon, which shows you have oscillation in space, with frequency is 1 over epsilon, or wavelength is all the epsilon. All right, a very small wavelength, where epsilon is small. You also have oscillation in time, because you have e to the I t over epsilon. So your solution is oscillatory in both space and time, and you have a lot of very small wavelengths, so lots of oscillations in your physical domain. All right. And typically, if you solve this equation numerically, you require, so here I'm going to use k, or I use these different notations. It depends on convenience. So both k and delta t represent the time step. H is the mesh size, all right, mesh size for x. So typically, if you solve this by, say, finite difference method, we require your mesh size to be little o of epsilon, which means for every wavelength, you need a few mesh points. You need many mesh points for each wavelength. You need many time steps for each wavelength, all right? So both mesh size and time step has to be much smaller than epsilon. So that's very expensive. So we know that if you, this is the Shannon sampling theorem. So you have a function like this. You want to say, if you want to plot this function, you compute this function. So this is like one wavelength. There are like 4 wavelengths here. You need a few grid points per wavelength to represent this function, right? So here you have like 7 or 8 points per wavelength. So imagine, so the mesh size has to be smaller than the wavelengths, much smaller. So when you have a lot of wavelengths, typically, the Schrodinger solution of Schrodinger equation is highly oscillatory. You have many wavelengths. And then you need a lot of grid points in every dimension. But you have very high dimensional problem. Imagine we have this Schrodinger equation several hundred of dimensions. And in each dimension, you have a lot of points. Then in a very high dimension, just this curve of dimensionality simply kills you, okay? It's impossible to solve a problem like this. So now the question, can you do better than this? So we have actually this very classical method. In the chemistry community, it's called Chautor splitting. In the math, we just call it simple splitting. So basically, you can split the Schrodinger equation. Remember, Schrodinger equation has 2 parts, right? You have this right-hand side, you have this kinetic energy part. All right, the second derivative of U. Then you have this potential part. So we can do opposite splitting. So the first time step, we solve this so-called free Schrodinger without this potential term. And the second step, I solve I forget about this second derivative term. I solve this potential term. All right, so that's called simple splitting. Now, for this equation, we can solve it by spectral method. It's discrete Fourier transform. If you take discrete Fourier transform of this, then this becomes minus, say, wavelength is cosine, minus cosine square U hat, right? And then in the Fourier space, this is ODE. You can solve it analytically. Okay, so you can solve I epsilon du dt minus epsilon square cosine square over 2 U hat. That's ODE. You can solve analytically. Then you do inverse Fourier transform. You come back to the physical space. You can solve this by spectral accuracy on the space. For time, you integrate exactly, no error in time. Second step is also very simple ODE. You can solve it by hand. You have solved it analytically again. All right, so you solve this for one time step, use that as the initial data, then you advance this ODE for one time step. That's called simple splitting. The accuracy is all the delta t. Okay, so it's a very simple method. Of course, you can do this strong splitting. You solve this step by half time step, this second step by one time step, then followed by another half time step of this first step. That gives you second order accuracy, that's strong splitting. All right. It's a very simple method, which is very popular in the chemistry community. Now you see, okay, so as you can see here, we solve this equation. And you plot the U is a wave function. If you take a modulus square, U is a complex value function. You take a modulus square, that's position density. As you can see, you have a lot of oscillations. Even this singularity is called caustics here, this large gradient system. You have a lot of oscillations. The next, if you take a U bar times gradient U, it's called a current density. That looks like this. You have a lot of oscillations. And if you, here we do experiment. If you use this Kronkon-Nicholson time spectral method, you can see if your mesh size is very small, time space is very small, you get a nice solution, all right? The solid line is the sort of analytic solution. And these oscillations are the solution for Schrodinger. However, you use a very large time step. Here is the time step is much larger than epsilon. If you use Kronkon-Nicholson time, you see get the wrong solution. So this dash is sort of a reference solution. And this part is your numeric solution. You get the wrong solution, you see this part is different from that one. Okay, same for the current density. So if you don't use small time step, if you use Kronkon-Nicholson in time, your time step is too large, you get the wrong solution. All right, and now I claim, well, typically, as I said, in typical classical method, you need a time step and mesh size to be very small, comparable to epsilon. You can prove this for this our method, this time splitting spectral method. You just very, very standard numeric analysis. You show that this analytic solution minus the numeric solution is bounded by essentially, so H is mesh size divided by epsilon to the power m. Okay, then here you have time step k divided by epsilon. So for the L to be small, your H has to be smaller than, much smaller than epsilon. This m is still has to do with the relative solution. So if typically if solution is C infinity and m can be any arbitrary integer, so it just requires H to be smaller than epsilon. This time it will be small. You need time step to be much smaller than epsilon. Okay, so that's why we require this. If you want to get the correct wave function. However, actually we can prove that if you just want to get physical observables, which means not wave function but the position density, flux, energy, and so on. Then for this time splitting spectral method, you only need time step to be order 1. So you can take time step to be independent of epsilon. So in order to prove this result, it's a paper I wrote with Wei Zubao and Peter Markovich a while ago. You have to use this tool called Wigner transform, which I introduced last time. So if you take, okay, so the Wigner transform between f and g is you multiply, you take a Fourier transform on f bar times g at different position, and you take Fourier transform on this sigma. You end up at a function which depends on x and also this Fourier mode cosine. All right. Then the Wigner, then f WFF. If f satisfies the Schrodinger equation, W is going to satisfy this Wigner equation, which is this linear transport equation corresponding to free Schrodinger. Then the potential term of Schrodinger corresponding to this scattering term here. All right. So from this, if you take epsilon go to 0, if you do Taylor expansion on this V, When you go to 0, you get this classical Liouville equation. So that's classical limit. So this is asymptotic transition from Schrodinger equation or with Wigner equation to the classical limit when you go to 0. So now we want to prove this discretization also has a discrete Wigner to discrete Liouville equation when you go to 0. That's what we mean by AP. So it's very simple to see, right? So first of all, assume spatially it's continuous. We don't discretize in space. We only use this splitting method for time, okay? Now you remember, on each of this step, if we do operator splitting on each step, we integrate in time exactly. So in the sub-step of the splitting, we have no error in time, which means if I take a Wigner transform on this splitting method, that corresponding to, if you take the splitting on Schrodinger corresponds to splitting of this Wigner equation. So the first step, we just take solve this transport equation operator. Second step, we solve WT equals this, because we have in each sub-step we have no error in time. So if you take Fourier transform on each sub-step, if we keep space continuous, essentially we have operator splitting for this Wigner equation. All right. So that's exactly this. Now for this, if you take epsilon 0, then this first term is the same because there's no epsilon here. Second term, if you take epsilon 0, then we know this operator, when epsilon go to 0, becomes this operator. So when epsilon go to 0, even you fix delta t, this operator splitting for Wigner becomes operator splitting for the Liouville equation. You can take the time step to be fixed. Okay, because and each sub-step, the time integration is exact. There's no error in delta t. So you can fix time step, send epsilon to 0, so you end up with the Liouville splitting for the Liouville equation. So this means we can take k to be independent of epsilon. All right, or fix take a time step. Then when epsilon goes to 0, our splitting for Wigner becomes splitting for Liouville equation. So that's what we mean AP in time. So this analysis, which is not rigorous, but give you the heuristics why you have this AP in time. Why you can take time step to be independent of epsilon. Of course, we cannot do this for space. Remember, we keep space continuous. If you do a discrete Fourier for space, and you take a Fourier transform, take a Wigner transform, you do not get this operator. You get an operator which you will rely on epsilon, all right? So we cannot get the AP in space. All right. So now it means we get accurate approximation for W Wigner function. Remember that if you take the moments on the Wigner function, if you integrate in psi, you get this position density. If you multiply, take the first moment of W, you get the current density. The second moment, you get energy. So if you get W right, you get all these moments right. So that's why we claim if you only want to get these physical observables, these guys, which are the moments of a Wigner function, we can take time step independent of epsilon. Okay. Well, of course, this is not very rigorous. Well, recently with Francois Gauss and Thierry Paul, we made this analysis rigorous. We can prove now rigorously that you can take time step independent of epsilon. And here, the analysis is a little bit involved, but we have to use this so-called Monge-Kontorovich two distance, which is defined here. Okay, it's basically if you assume the rho and rho prime, which are the for both Borel probability measures. So this is the distance, Monge-Kontorovich two distance between these two probability measures. Okay, standard definition. But this pi is joint distribution, and if you take a marginal pi with respect to p and q, recover one of these marginal distributions. Okay, so that's what this definition means. So it's standard notation for Monge-Kontorovich or Wasserstein distance with in the L2 framework. which Francois actually introduced a little bit in his lecture. And then essentially, if you define so-called the Husimi operator, so here this is the Wigner transform, all right? So R is the density matrix. You take Fourier transform, it's the Wigner transform. And now if you take a convolution of Wigner transform with the Gaussian, so if you use the operator form, so it's basically you evolve this sort of free, it's like free Schrodinger operator, but it's Gaussian, all right? This is Gaussian. With this Wigner transform, that's Husimi operator. And then we can prove that this multi-conservative distance between the Husimi of the analytic solution, analytic density operator, and this numerical one, basic operator splitting, is bounded by the right-hand side, where you have this time step. And here you have h bar, which is epsilon, square root of epsilon. And here, this is just constant, which depends on time and also this potential. All right, you need some regularity for the potential. From here, you see that you get air, which is bounded by delta t plus square root of epsilon. All right, so no matter what epsilon is, you can take delta t to be independent of epsilon. And from here, actually, once you have this estimate, then if you combine with standard air estimate for fixed epsilon, you end up at air which is uniform in h bar. So indeed, we can prove this spectral operator splitting spectral method. And this norm, okay, you have air which is uniform in h bar, but only for delta t, okay? So that's a rigorous proof of AP in time. Then you want, how about spatial discretization? It turns out it's impossible to take time and mesh size to be order 1. The best one can do. Well, before in the previous method, I showed you that x has to be order epsilon. But it turns out that the best one can do is take delta x to be square root of epsilon. And it's not a very trivial method. I mean, you have to use the so-called Gaussian beam or Gaussian wave packet methods, which was originated by some works in chemistry and also in seismology. Okay. So the idea of a Gaussian beam or Gaussian wave packet method is write a wave function to be by its amplitude times e to the I times the phase over epsilon. Okay. This looks like a WKB ansatz, but it's not exact WKB because here this phase depends on t time, axis position, and also y. What is y is called the center of Gaussian beam or Gaussian wave packet. So this t, if you take a Taylor expansion of around this y, the center beam, the leading order, the next order, second order, and you ignore the term beyond second order, you stop here. And this M usually is a Hessian matrix, all right? And you plug this ansatz, into the Shortening equation. You throw away this higher order term in the truncation, in the Taylor expansion, and also higher order term in epsilon. Then you can get an evolution equation for this y, which is the center of this Gaussian beam. And also this is like a momentum, and also this Hessian matrix, okay? And this S is the phase, where A is amplitude. A here is complex value, and T is complex value. To get this system of ODE for all these unknowns, amplitude, and its phase, momentum, and Hessian, and you solve this dynamics, then that governs the evolution of this ansatz, okay? And if you only do geometric optics, you only have this this part, this first line. That's like geometric optics. You have classical particles. But here we evolve this Gaussian wave packet. Okay, so that's different from classical geometric optics, okay, or WKB. And you evolve this Gaussian wave packet, okay? And here there are some key issues. Remember here, this M, the Hessian, actually solved this is a Riccati equation. Okay, right? dm dt equals minus m squared. The Riccati equation we know typically blows up in the real space. You have singularity, which corresponding to caustics in geometric optics. However, here M will be complex value. We choose M to be complex value, okay? And it also has a positive, definite imaginary part. And if you have a positive density imaginary part, and you plug it here, that's why this thing will look like Gaussian, okay? Because the imaginary part of this is positive definite, so you get e to the minus something, which looks like Gaussian. That's number one. And number two, if it's a complex valued Riccati equation, actual solution does not blow up. If m is the complex value, that solution to this will never blow up. Okay, that's another feature of this Gaussian beam method. And so that's the idea. So you have a lot of Gaussians. Each Gaussian will evolve in time according to these dynamics. Okay. And then what happens is that first, if you start with general initial data, which is not Gaussian, you have to decompose initial data into a superposition of Gaussians. Because we saw Schrodinger equation is linear, so it certifies the linear superposition. So if you start with any general initial data, say if it's WKB initial data, okay, you do a linear superposition, you superimpose this initial data into a summation of a bunch of Gaussians. So that's why you have this integrating. Y0 is the center of Gaussians. All right, so you evolve each of these phi I, this Gaussian beam sinusoids, for all these Y0, which are the essential centers. You essentially have to add all these Gaussians. All right. So you have involve many Gaussian beams, like many particles. And if you start with initial data like this, and evolve according, you superimpose into a lot of Gaussian beams centered at the Y0. Okay. And then you involve these Gaussian beams to some point. In the end, you have superimposed all these Gaussians. You have integrated Y0 again to get your solution to the Schrodinger. Each individual Gaussian beam is not a good approximation to the solution of Schrodinger. But if you superimpose all the Gaussians, you end up with a good approximation to the Schrodinger. Okay. So that's the idea. However, there's some issues with this method because each Gaussian has to have a support, which is square root of epsilon. But as time evolves, I mean, the support may increase in time. So some later time is no longer, support is no longer so narrow. They have to reinitialize. You have to add them and reinitialize, okay? So that's the pain, a little bit of pain. But here, to take Taylor expansion on the phase to the second order, particle can expand Taylor expansion to higher order to get higher order Gaussian beam. And in the end, you can prove this method actually works, converges. Essentially, you get a Gaussian beam, all right, solution has accuracy, which is like a square root of epsilon to the power k, where k is the order you expand in this phase to Taylor expansion. You expand with higher order in k, then you get this k over 2. Okay. Standard Gaussian, the beam I just showed you has an area square root of epsilon, where k equals 1. But you can expand to higher order. So you get this kind of accuracy. All right. And because the Gaussian beam support, each of Gaussian beam has the width of square root of epsilon. And to resolve this, each Gaussian, you need time step, I mean, spatial delta x to be square root of epsilon. That's why for this method, delta x is order of square root of epsilon, but not epsilon. Okay. So there are different versions of this. For example, this is we do Taylor expansion, right? You truncate. But it's a nice version by Giovanni Russo and Peter Smerica, where they have some non-truncative Gaussian wave packet mass transform. You arrive a similar method, but it's not truncative, so it has a little bit better accuracy. Okay. And also, as I mentioned, this Gaussian beam you need to reinitialize because eventually the Gaussian beam becomes too wide. You have to reinitialize. So there's also this phase space. This frozen Gaussian beam, which is defined in the phase space. There, the width of Gaussian beam is fixed, like this. So you expand the general wave function into of this form, all right? So then you have this fixed Gaussian profile. So Gaussian profile has a fixed width, but you have to go to the phase space, all right? So that's also an original idea due to this chemist Heller and Hermann Krug. And more recently, this work of Jianfeng Lu and Shi Jin, who had built some rigorous mathematical foundation for this frozen Gaussian beam. And here's some comparison of a numerical result. Okay, so here's the solution, which is highly oscillatory, the solution of Schrodinger. And if you use the standard geometric optics, you get nice accuracy here, but around caustics, you get very bad air accuracy if you geometric optics. But if you do Gaussian beam, you get a uniform accurate solution, even around caustics. Okay. All right. So that's what I want to say about this transition from Schrodinger and to classical. And if you are interested in this topic, there are two references, both in Acta Numerica. One is about 10 years ago. It's a rather comprehensive review of all these semi-classical methods. The paper is a review article written by myself with Markovic and Christoph Schwaber. And last year, there's an updated version, which is a little bit different. It's more emphasized more on applications to surface hopping problem. It's written by Christian Lubisch and Caroline Lasse. So you can read these two reviews. All right. So that's the end of this story about this Schrodinger. So now I have to. Any questions at this point before I go to the classical mechanics? All right. So I get my slide. Let me see. There's some questions. Because we kind of shocked by how much the result changed from torus to not torus. Torus, you mean a periodic bound condition in space? Is that what you mean? The gentleman Leopold Truman. Yeah, well, it's a very good question because here we use spectral method, which means we use periodic for the first method, right? Time splitting spectral method. To use spectral method, we have to, at least for a spectral method, we have to assume periodic bound condition. And of course, if you don't have periodic, we were talking about a solution which say has some complex Bohr, and its wave function in finite time assume our computational domain is large enough, so the solution is essentially zero. So we sort of use periodic bound condition. But if you don't have this, if you have boundary problem, then it becomes complicated. You might have used some transparent absorbing boundary conditions. All right, so that's of course more challenge. But for the Gaussian beam method, we do not need these periodic bound conditions. Okay. So that's my answer. Is that okay with you?